part, you got to show at the end here that the statement is true at, now can someone in this class tell me, if I'm assuming it's true up to a certain point, but I'm not satisfied there, is it now true at the next? And then the next. What would be appropriate to write here to show the statement is true at what, if I'm assuming it's true at k, what might be appropriate to write as it's true also at k plus 1? We keep going, one more. So n is equal to k plus 1. Wow. That's step 3, we got to show those two sides are going to be equivalent here. But first, guys, I got to see what the statement looks like at k plus 1. Here we go. We got 2 plus 4 plus 6 up to 2k already. Do that so you see that. That's up to 2k. But you say, no, Professor, you got to show it also now is true for the next step, which is k plus 1. If I replace n by k plus 1, that looks like this on the left. So the blue has been extended by 1. Now the other side at k plus 1, replacing n by k plus 1, you get to k plus 1 here, and k plus 1 gives me k plus 2. That's what they mean by showing the statement is true at n is equal to k plus 1. If I can show those two sides are equivalent, we're finished. But before I jump into it, it's going to be very simple to finish this up. Since this is the only induction proof I'm doing. Start out with showing it's true at n is equal to 1. That means the first term is equivalent to replacing n by 1 here. It's true. Now you assume it's true up to a certain point, and they call that certain point k. So put a k here, k here. It looks like this. The next step is the big step. Now show the statement is true at now next k plus 1. That means extend this to k plus 1, which looks like this, 2 times k plus 1, and then k plus 1 on this side. Is that making sense? The way we have written. If I can show those two sides are equivalent, we're finished. Now, you say, Professor, well, see. Step 2, this part in the blue from step 2 is already equivalent to what? Well, step 2 say at least that much is equivalent to right now from step 2. Is that k times k plus 1? That's step 2. Step 2 directly tells me that. I still have this on the end to add to that. Now keep in mind, I got to try to show all this eventually is this. Does anyone see anything happening at this point that might help me to show, Professor, those two sides are the same? And we'll be finished. I see one or two things you could do. You could expand this out. I'll show you what it would look like. If you expand this out on the left, you're going to have k squared plus k. And down here, it looks like maybe 2k plus 2.
Can we factor the group?
Thank you. We'll go back and do that also. If you should expand it out, and I've had some students who expand it out, like terms you're actually looking at on the left-hand side, k squared plus, what is that, 3k plus 2. If I clean the left-hand side up. And guys, I think if you factor that, will it factor into this? Will this, after I clean the left-hand side up, I cleaned it up, will this expression now factor into this?
Yes.
And is that equivalent to this side? And we're done. As soon as you can show that. Alexandra and other students saying, Professor, I saw a quicker way on this particular one. You would not necessarily have to expand this out. Why not just take out a common factor of at the very beginning of how much? This is an alternative. Take out k plus 1. So if you had pulled out a k plus 1 on those two terms, would that lead you directly to k plus 1 times k plus 2, this? And you're finished. And that's the induction. They call it induction proof. Try to show the two sides are equivalent. Guys, since that's the only one I'll be doing, how's it look? If you saw something like that, could you do it for me? The 3 steps. If I kept it very, 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 very simple. Okay. Done. We'll accept that. In fact, it might be that one on the test. If it's there at all. Okay, now, Shane?
Yep.
I know what's coming up. This is sort of getting us close to the end here.
Binomial.
Binomial theorem. And I thought the best way to approach this is reflect back. And I think when I reflect back, every student in this class, I think have seen this before. Binomial expansion. Now guys, watch carefully. I'm going to make a real quick lesson of this, and then we'll be finished with chapter 11. Binomial expansion, we start out with this. Can anyone remind me, if I take a binomial, 2 terms, not trinomial, binomial, and I raise it to, let's start out with raising it to a 0 power. If I say expand that out, anything raised to the 0 power should be 1. If I now take that same binomial and raise it to the 1st power, it merely becomes a plus b. Same binomial, a plus b, raised to the 2nd power, expanded out, would be merely this to work with. Can someone tell me what you think, if you were asked to expand it out, what a plus b times a plus b times a plus b might give you?
A plus B.
Well, I want the final answer. A plus b times a plus b times a plus b, give me a guess.
Is it not this?
Give me a guess first, and I'll get into my routine here. A cubed for sure, I'll accept that.
3A squared.
Wait, you're saying 3a squared?
Times
B, okay, plus
3A times B squared. Plus B squared. B cubed.
Mr. Hahn, he's telling me, Professor, don't multiply it out. We just got limited time tonight. A plus B times A plus B times A plus B, Professor, I think is that. I want to sort of close this down, eventually try this. A plus B raised to the 6. Now, I don't think Mr. Hahn's going to give me a quick answer this time. But it's A plus B times A plus B times A plus B out 6 times. Looking back for help here, I'm not going to multiply all this out. Take too much time here. A plus B raised to 0 is 1. Guys, I'm going to pay attention to these coefficients. They're going to play a part in my little process here. Now watch what happens. I know you've seen this before. On the side here, to eventually get down here without much effort, I'm going to go back and look at what we have. We got A plus B raised to 0 is 1. I'm going to take that 1 and place it right there. A plus B raised to the 1st gave me A plus B. 1A, 1B, I'm looking at the coefficients. I'm going to place those like that. A plus B squared gave me this, which is 1, 2, 1 for the coefficients. Mr. Hahn, I'm going to accept what you gave me. He gave me, for this one, 1, 3, 3, 1. I'm going to place those coefficients like that. I'm building a triangle with those coefficients. Another mathematician's name. Pascal's triangle. He came up with this in the experiment he was doing. Guys, there's a pattern here. if you look at it closely, that you should be able to tell me what the next layer of numbers might be.
1, 4, 4.
Okay, I'm hearing 1 for sure. I heard what else? 4.
4, 6,
6.
4,
4.
1.
1. Now I should, I'm going to tell you what that little process is I'm using. I should be able to tell now what the next layer would be. But definitely common sense tells us it's going to end with 1s. Now what's in between? I heard 5, 10, 10, 5, 1. Can I continue? Of course I could continue to another layer, another layer, another layer. Now if I'm going to eventually do this, a plus b times a plus b times a plus b out 6 times and do it fairly quickly, I have to decide which layer I need for this particular problem here. Let me write out one more layer. 1, 6, 15, 20, 15, 6, 1. You guys agree?
Mm-hmm.
Now, does everyone see what I'm doing to get those numbers? I'm going back to the previous layer. 1 plus 5, 6. 5 plus 10, 15. 10 plus 10, 20. 10 plus 5, 15. 5 plus 1, 6. And of course, they start with the 1 and end with the 1. And that's how those numbers are coming about. Now, I got to keep in mind, though, since I'm after this one, that this 1 represented this. These coefficients came from this. This represented this, the blue here. These coefficients represent this. Of course, I go ahead and write this out. And please tell me, do not let me leave something out. Does this last layer represent a plus b raised to the 6th, at least the coefficients?
Yes.
That true? So now I know my coefficients of this. Now, if I say now, let's write this out. Okay, a plus b raised to the 6th, guys, I can get some space here. Now, before I write the terms out, write quickly without taking the time to multiply a plus b times a plus b out 6 times and we're here all evening. First observation, for an example, a plus b cubed, I had 1, 2, 3, 4 terms in the answer, in the expansion. A plus b squared, I had 3 terms in the expansion. How many terms would you expect for a plus b raised to the 6th? 7. So I could say, well, I'm getting ready for 7 terms. Let me count. 1, 2, 3, 4, 5, 6, 7, I think. Is that true? Let me get my coefficients out of the way. You'll say, Professor, where are the numbers? You've got numbers here to worry about. These are my numbers from the triangle. So just pull those numbers out, put them in. 1, 6, 15, 20, 15, 6, 1. Now, guys, I need, those are my coefficients, those are my numbers. Now I need A something, B's will come in. What would you expect A to be in that first term? 7. A to the 6, not 7. A to the 6. I would think now, A to the 6 is going to start me out. What might be A in the second term? A to the 5th, it's going to drop down. A to the 4th, A cubed, A squared, A. Now the B, I notice there's some B's over here. I might do this is me. On the end, I know for this one, it must be B to the what? 6. Is that true? Therefore, if it's B to the 6th on the end of last term, the previous term must have been B to the 5th. B to the 4th, B cubed, B squared, B. there's your answer. You're finished. That's A plus B times A plus B times A plus B, with the help of this binomial expansion and Pascal's triangle. Guys, for a quick check, we're finished with the expression. This right here is equivalent to this. Quick check, it was A plus B raised to the 6. I see a 6 exponent here. In my second term, I see 5 plus 1, 6. 4 plus 2, 6. 3 plus 3, the next term, 6. 2 plus 4, 6. 1 plus 5, 6. The exponents are all 6 all the way across, which they should be. And then I have my coefficients. And you're done. You're finished. Now, please tell me, you have seen Pascal's triangle before. Definitely you have. Well, you have seen it now. Okay. To work with. Now, I think though for us, they call this now not binomial expansion, but doing the same thing they did back in middle school. I've seen middle school teachers do this, and kids love it. Students in middle school love this. They just go to the triangle and pull out the numbers. They have no idea what they're doing, but they just pull out the numbers. The teacher smiles, and they smile, and everybody's happy. They just give them the triangle. They just use the triangle and do it. Your textbooks, though, you're in pre-calc. They call it binomial theorem. I said, wait, Professor, are you telling me before what we did by middle school, if I see one of these on the final exam, Professor, and I do it like you just did here, like in middle school, and write the triangle out for you, will you be happy? No. Can you get the answer to doing this? Yes. But suppose I ask you on the exam to take A plus B raised to the 50th. Good luck. Good luck. So your textbook changes into, from expansion, they use the vocabulary, terminology. They now say, no, there's a theorem that they should know. And guys, it's going to look strange for us to close this down. To expand by using a theorem. And they call it binomial theorem. Ignacio. Hey, Ignacio, you know range is good. I'm good at making lessons connect. Ignacio, tell the class, for example, on this one. In fact, on this one. Are these terms separated by a plus sign?
Yes.
And that adding, that's what it is, add. Does that mean summation?
It does.
That means somehow they're going to rewrite this using sigma that we were doing before the break. Now, when I write this formula up for you and start using it, I may use some notation I have to slow down and explain here, but they're going to say, no, please, Professor, are you kidding? All this can be written as a summation. Now, with limited time that I have here, I'm going to just jump right into it, write it out. It's going to look strange. Then what to explain to you, or what do I have to explain? What on earth the theorem's telling me. They call it binomial theorem. And then I'll go back and apply it and show you how to use it. And then when you leave me, at least you've been exposed to it. Shane, I think, did I write somewhere there what the binomial theorem looks like using the sigma? A plus B raised to the n, probably.
No, we've got the notation needed for the presentation.
Oh, you got the notation. Okay, let me write this out. Since I am limited on time here. Let's do this. Oh yeah, here goes. They write it as summation.
I lied.
Oh, it's on there?
Yeah, it's here.
What does it look like?
X plus A to the n.
Oh, they got x plus a. Okay, I'm gonna stick with a plus b.
Okay, A plus B to the n.
Okay.
Summation to n.
Okay.
Starting at 0.
J is equal to 0.
Yep.
Up to n, you said.
Mm-hmm.
And inside there is something strange. What is it?
It's an n above a j.
Thank you.
No separation. Times, oh, that would be A, I guess.
A.
A n minus j.
Beautiful.
B j.
Wow. What a way to close down class. What a way to close down class. You're at Stanford now. You don't see Stanford do this. No, when they talk about binomial and binomial expansions, yeah, this is middle school, I like it myself, just to move into what we're doing here, but they're saying, no, Ignacio already said, wait, Professor, I see plus signs over here. You're adding, so let's use a sigma, and that's what it is. Now though, Shane, to break this down to see what on earth does this mean, first, I need to explain first, for a reason, what this notation means if you see it in mathematics, and with an exclamation.
It's allowed.
Is it Ian's excited about being in math? No, it's read as n factorial. Now, tell me on the handout, did I have a chance to write down what n factorial meant?
Yes.
Did I start out with n times n minus 1, n minus 2 down to a 1? Okay, that's what it means. Need that to show you the translation. And go to multiplication down to 1. That's what the n choose j shortly will mean to do. N factorial, yeah, I got an n to worry about. That's no problem. Guys, before I leave the n factorial, let me try an example here. If I say, what is 5 factorial in math? If I use the formula, it says start out with 5. N minus 1, in my case, would be 5 subtract 1, 4. 5 subtract 2, 3. And continue until you reach 1. Now, that would be, in my case, guys, what is that? 5 times 4 times 3, help me out, times 2 times 1, yes or no?
Yes.
And right quickly, is that 120? Yeah. So 5 factorial has a value of 120. So you can easily find a factorial. It's not hard to find. Accepted though, which looks like look a little strange here, they accept that 0 factorial, which is in case you haven't, is 1 by definition. I will not argue with the definition. They say it's 1 by definition. They also say 1 factorial, which makes more sense, is 1. But they do accept 0 factorial for a reason. It's also 1 by definition. Okay, Shane, with that said, I think I now need what n with that j there means, and then I'm going to apply it to my problem there and accept that as the binomial theorem. Let me do this right quickly, because your course is almost finished here.
Does n over j mean n choose j?
There you go.
Okay.
It's on the side here. This notation, which is part of that theorem, means, sure enough, n choose j. Now, let me first translate myself what that might mean. And I think there's a formula for it on the handout. But first, let me give you a translation. I suppose for some reason at the end of class, I say, guys, I need 2 volunteers to help me with something. And I need some volunteers to help me, and I need 2. And all of a sudden, I see 5 hands go up. Oh, Professor, I'll help you, which whatever you need down at the end of class. So I've got 5 people who are volunteering. I just need 2. Written like this. This is a little translation of what this means. I have 5, but I need only 2. 5 choose 2. 5 people, I need only 2. Now, me, as an instructor, I got to come up with how many different ways can I choose 2 out of those 5. I may choose Billy, Alexandra. I may choose Ignacio, Mr. Hahn. I want to know how many different possibilities will there be for me if I have 5 volunteers and I need only 2, if I choose 2. And I'll give you a formula to find out. But first, let's label in this case those 5 students like this. Those are my 5 students. I'm choosing 2. One possibility is I could choose student A and student B. That's one choice. Or I could choose student A with student C, or student A with D, or student A with E. Are those choices? If I need only 2 students of the 5. Are there other ways I could choose the 2 that I need? Yes, there are. I could choose B with C, B with D, B with E. Number 8. Guys, what am I leaving out?
C.
C with D. Possibility. And since she gave me that, C with E. Another possibility. I think there's one more and I may be overlooking it. What is it? D and E. And I think those are the only possibilities I have. Is that true? How many possibilities did I come up with? 10. I'd like to be able to calculate that I would have 10 without actually listing all of them and counting. 10 directly from here. And that's what the formula does for me. Tell me, please, on this, Shane, what was n choose j as a formula?
N factorial
N factorial.
over j factorial times n minus j factorial.
There you go. Okay, guys. Let me go back to my 5 choose 2. I actually listed these. We have 10 possibilities. So let's see if I get 10 by using this formula. It says n factorial. In my case, that's 5 factorial. J factorial, 2 factorial. That's the j right there. N minus j, 5 subtract 2 factorial. 5 factorial by factorial definition is 5 times 4 times 3 times 2 times 1. 2 factorial, 2 times 1. 5 subtract 2, which is 3. 3 factorial, 3 times 2 times 1. If I write the factorials out. Simplify this, guys. I see a lot of canceling going on. All of this will cancel. 2 into 4 would cancel, so I end up with 5 times 2, 10. And that's exactly what we end up with for 10 possibilities of choosing 2 students from 5. Is that true, guys? So now I have another formula as if you need another formula at this time. It looks like this. Whew. Now, let's finish this up. Here's the binomial theorem. I want to redo a plus b raised to the 6. Here's the answer. About Pascal's triangle, I'd like to rewrite a plus b raised to the 6, now using this. Okay, here we go, guys, on the side. A plus b raised to the 6 is equal to, by the binomial theorem, I always start with a 0 for the j. Use the j here. N in my case would be 6. It says now n choose j, that would be 6 choose j. You guys agree? Next says a raised to the n minus j. In my case, a is, or a raised to what? N minus j, 6 minus j. Let's put 6 there, since my n. And b raised to the j. Is that the way it looks with the binomial theorem? Did I put everything in correctly? If I put things incorrectly on the binomial theorem. Here's the binomial theorem. Here's my problem I'm trying to do. Did I write that out correctly using that? Who on earth would think, Ignacio, especially equivalent to this? That little piece over there says this. Now, am I going to write out all those terms again? No. Okay, here goes, and I'm finished with the binomial theorem. Can anyone be wise and help me to close down? I'd like to, with your help, 1, 2, 3, 4, 5, find the fourth term. 1, 2, 3, 4. Here's my fourth term. Right here. Where's my fourth term in the expansion by Pascal's triangle? Can anyone tell me a way to find the value of the fourth term? Maybe fairly quickly using this. Or maybe first we should write the first term. Okay, got you. Here we go. Let's write the first term first. Guys, it says start out with 0. So if I replace j by 0, I got 6, choose 0. They say start with 0. A raised to the 6 minus 0, b raised to the 0. Is that the way the first term would look? Let's try the second term. What would the second term look like with the help of the binomial theorem? Now 6 choose what? 1. I got to build up to 6. A raised to the what? 6 minus 1. And b raised to the 1. I'm going to write out the first 4. Next one looks like this. 6 choose 2. A raised to the 6 subtract 2. B squared. And my fourth term, since I'm going to stop with the fourth one here, would be what? 6 choose 3. A raised to the 6 subtract 3. B cubed. Now keep in mind there are other terms out here. Is that true? Is that the pattern there? Now I'd like to, just to close this down, I know it looks a little strange with that n choose j and all that business tonight. I'd like to calculate what this looks like. Just this term here. Which is 1, 2, 3. Is that my fourth term? I'm going to use expression there and do it. It should be equivalent to 1, 2, 3, 4. Pascal says it's equivalent to this. So it should be the same answer. So the fourth term here by using the binomial theorem should be equal to that fourth term in Pascal. Guys, if it is, here goes 6 choose 3, that's 6 factorial, over 3 factorial, over 6 subtract 3 factorial. I said, Professor, what did you do? I probably used this formula here. Didn't I? N choose j? Did I apply that formula correctly, guys? Right here, 6 choose 3, is that done correctly by using that formula over there? Okay. And then a raised to the third, that's easily done, and b to the third in this case. Finish this up. 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. Done. Bottom part, denominator 3 factorial, 3 times 2 times 1. 6 subtract 3, which is 3. Another 3 factorial, which looks like that. Is all that true? Cancel as much as I can. Well, all this will cancel out. This will cancel out. Oh, guys, here goes. Can I cancel 3 into 6, if I wish, get a 2? Cancel these 2 out. Is that true? And what am I going to end up with? Anything else cancels out here? So,
20.
is that 20?
Yeah.
And it looks like it's going to be 20, what was it here? A cubed, B cubed? Is it true? Now looking back at my fourth term over here, 1, 2, 3, 4, what is that showing us that? Was it 20 A cubed, B cubed? And get the same by using the binomial theorem. Billy, class, you leave me. You're going to start crying first. But wait till you see that math 7. They're not going to play around. I don't play around when I teach that calculus. This is the binomial. Don't expect that teacher to show you this that Ramsey showed you, where it came from. No, they're going to say this is the binomial theorem. Accept it, use it, and move on. Okay, Shane, did I do anything else with that? Or are we finished with chapter 11?
Finish with chapter 11.
We're finished with chapter 11.
Just got-
I cannot believe I did it. Now, I did a few little items on chapter 9. A few, Billy knows that. Few little items before you leave me. I've got time to show you what it is. I just want you to point out that some curves that you might witness in Math 2, Math 7, and Math 8. Some curves that we have not done in this class. We've done a lot of graphing in this class. But, I'm gonna erase this, guys, by the way, does all this make sense in the presentation? That binomial theorem looks so strange over there, blocked off, that's theorem itself, but it works. Now we'll finish this up quickly. First, I'm going to start out with this. I'll change it to 16. All of a sudden, you're a Math 7 instructor or Math 8 instructor, I think that's Math 8. Says we got to do some calculus on this curve. You say, curve? Yeah, did Randy show you what that cracks into? So guys, if I look at that, is it going to be a parabola? We've done a lot of parabolas in here. Is it going to be a parabola? No. It's going to be something we have not seen before. Some of us may have seen it elsewhere. Does anyone recognize the way it looks, what this might graph into? And I just want for tonight give you what the shape looks like.
Ellipse, just
I heard ellipse. Now, if we say ellipse, the oval shape. Wait till you see what you're going to do with it in Math 8 when you find it. Right, Mr. Park? Okay, when they finally ask you to draw the ellipse, and then they're going to say, no, do some calculus on the ellipse. Me, I just want to graph it right quickly. And if I graph it, get a quick shape. I'm going to close down here. Okay, anyone look at that and tell me right quickly, where are the x-intercepts?
2,
Where are the x-intercepts? Don't scare me. This is last night.
Negative.
How do you find x-intercepts? You replace y by 0. If I replace y by 0, this term drops out. And you're left with merely x squared is equal to 16, which is plus or minus 4. So I know the x-intercepts. I got a negative 4, a 4 here. Now, can someone quickly tell me where are my y-intercepts? Absolutely, replace x by 0, and you end up with y is equal to plus or minus 2. Here. And here. Now, without even taking the time to replace by 0 this or 0 that to find the x and y intercepts, which I like, my gosh, guys, this is what, 4 squared? And this is a nice square, it's what, 2 squared? So I could actually see my x-intercepts right there, 4 and negative 4. I see a 4. And down here, what? A 2 for the y. That's another quicker way to find what they are. I think, Ignacio, you tell me if I connect these points and not connect anything else. Are you telling me it may look something like this?
Yes.
A football shape? And that's the ellipse. Done. So after you leave me, if you recognize that and they say, we gotta do something with the ellipse, you'll know at least what it looks like. That oval shape. Can anyone tell me, might an ellipse turn into a circle?
Yes.
If what happens?
Bases are equal.
If these two denominators are what? Equal. So that ellipse is going to turn into a circle. My last one here, guys, and I wish you the best. Number 2. Now it looks like this. Watch carefully. Now I'd like to know what that shape might be. I put a subtraction sign in between. And so, wait, Professor, I saw what you did back on the ellipse. You asked us to find the x and y intercepts. It worked out so nicely for me. You connect, you get that oval shape. So guys, if I try it on this one, now watch carefully. Your instructor has done it. He's finished the course up for you. Where are the x-intercepts on this one? Are they still 4 and -4? I'll mark that right here. Mark that here. So those are my x-intercepts. Oh, you said, Professor, my goodness, you just, looks like what you just did there. Where are my y-intercepts?
Just the two.
Up again? Who wants to be exempt from the final? Yeah, I see hands going, oh, I'd like to be exempt from the final, Professor. There are no y-intercepts on this one. Why? If I replace x by 0, which I'm supposed to do, that term drops out. Then you attempt to find the y, you can multiply both sides by 4. If you multiply both sides by 4 after that first term drops out, are you going to end up with this eventually? Or better yet, are you going to end up with this? Eventually. And then you're going to do what? You're trying to take the square root of a negative. Impossible. There are no y-intercepts on this one. You say, wait, Professor, what am I going to do then? I'm going to turn my paper in at Stanford, just have those 2 points, and have them laugh at me? I said, where'd you come from? Don't tell me you came from Ramsey's SMC class. No, just turn it. What's the graph? This point and that point? Bella, don't you do that at USC. Okay, here we go. No, you know better than that. But I'm going to do this. I'm going to use those numbers, 2 and -2, not as y-intercepts, but I'm going to use them in graphing this. You guys move up to 2. But I will not treat them as y-intercepts. But they're there. Now, your textbook gives a strange approach to this to get the graph. And some students may recognize what the graph's going to look like. The last one was an ellipse, oval shape. They ask you to do this. Construct a rectangle through these points, because that 2 is not representing a y-intercept. Line up for me. And here, and here. So wait, first draw a rectangle connecting those points. Strange process, but it leads to the graph. So we can do that. We can draw a rectangle, connect the points, but don't turn that in at USC. That's not it. We're not finished. Now, where's the graph, Professor? Now they ask you in this little technique, draw the diagonals of that rectangle. I'll just do it free-handed. Just draw the diagonals of the rectangle. You guys look like this. Through the origin. And it comes out through the corner. There's one of the diagonals. Draw the other diagonal. Through the corners. Like that. So, oh, it's kindergarten. That looks so cute. Don't turn your paper in yet. We're not finished. Oh, where's the graph, Professor? That looks so cute, though. Kindergarten stuff right now. Where's the graph? One piece of the graph's got to pick up this point. Another piece of the graph's got to pick up this point. They're going to be separate. And wonder what those diagonals are acting as. Asymptotes. So in other words, if I pick up this one over here and follow as asymptotes those diagonals, one branch will look something like that. Where's the other branch? It's on the other side, picking up -4, which it's got to pick up, and follow the asymptotes there. And there's your graph. Does anyone think they know the name for this graph? It's called a hyperbola. So those are the two most common graphs that usually don't work too much with. But in case, ellipse, hyperbola, at least you know what they look like, the shape, and maybe a just simple one drawn. Your course is over. It's done. Shane, I don't think I have anything else there, do I?
No.
Friends, he did it. But you're not done yet. The course is done, but you're not done. Guys, the last few minutes, Mr. Park,